Hello, this is Jack Jackson. In this video, we're going to look at a triangle similarity criteria. Let's just review that two triangles are similar if and only if all the corresponding angles are congruent and the corresponding sides are proportional. Okay, so ratios of corresponding sides equals some constant. Another way to say that last condition is that all of the sides in the second triangle are that constant k times the sides in the original one. So if these are similar, angle A prime would be congruent to angle A, angle C would be congruent to angle C prime, angle B would be congruent to angle B prime, and if this side is length A over here, it will be A prime will be k times A, uh, B prime here will be k times B, and C prime here will be k times C. That's the definition of it. Okay, and we have an earlier basic result that kind of takes a little while to prove, but is the angle-angle triangle similarity theorem. And we determined that if we could just get two angles that correspond to be congruent, then the two triangles must be similar. Okay, so the question is, are there other criteria of things? And so we're going to examine in this video the SAS situation. So what that means is we're given triangles so that angle A and angle A prime are congruent. In this example, we can control that with this slider here. All right. And then we can just change the lengths here of these sides here to be anything we want. And then we can change this factor so that we can make these sides longer or shorter in the second triangle. And each of the sides, the blue side down here, A prime to B prime, is k times the distance from A to B. So if we call the distance from A to B C, then this is k times C, and right now k is 2.8. Okay, and then this side B is 2.8 times this one. So that's all we're given. And the question is, do we get the other parts of similarity for free? Do we get that the other angles are congruent and that other side is also k times that this side right here from C prime to B prime is k times the distance from C to B. So is that true or not? Well, you can look at the measurements here, and it does turn out that the angles are congruent. And if you look down here at A prime, there's its distance there, and it does turn out to be k times the distance for A as well. So it does seem to work. Okay, and if we change this, yeah, it does look like those angles are measuring up correctly. We know from the angle theorem that is enough. Now, by the way, I have this thing constructed so that these sides here are parallel to the corresponding sides. I just did that for convenience. That's not something that would need to happen. You could, if you rotated this figure down here, it would still be similar. It wouldn't change anything. So no matter what we do to this figure here, the other one is just in such a way, and it does always appear to be similar. So it looks like we do have a side angle side triangle similarity theorem. So what would that theorem say? It would say this: given two triangles, triangle ABC and triangle A prime B prime C prime, with angle A congruent to angle A prime, and A prime B prime, that distance over the distance from A to B, is equal to the distance A prime C prime over AC, as we could call that K, then triangle A prime B prime C prime is similar to triangle ABC. That's what we think happens here. Let's see if we can prove that. So if we slide this slider, we can go through the proof one step at a time. Okay, so the first step is set up our given. We're given two triangles, triangle ABC and triangle A prime B prime C prime, with angle A congruent to angle A prime and A are congruent. And let's let K be this constant, A prime B prime over AB, and that's equal to A prime C prime over AC. Now, what if K is 1? Well, let's adjust this so that K is 1. Well, if K is 1, then what happens is these two triangles actually are congruent. Right there, see that they're congruent. And so why is that true? Well, because of the side angle side postulate. So we've got that case covered. So let's assume K is not 1. Now, it really doesn't matter which one is the biggest one, but let's assume that the biggest one, that the K is bigger than 1. Let's say, let me set it like 3 for right now. Okay? So K is bigger than 1. If there's K is not bigger than 1, we'll just relabel these guys up here with primes and these without the primes and then proceed that way. Okay? So we can do this without loss of generality, and so this is cool. We can do this. So the basic idea of the proof is to take inside the first one, make a congruent copy of the original one inside that. Okay, so here's how we're going to do that. Okay, start by going out on ray A B prime. We can go out any distance we want, and we can go out the distance I'm calling C, which is distance from A to B. So now we want this distance here and this distance up here will be congruent. Notice if K is bigger than 1, that'll put B prime between A prime. This is B double prime, and it'll put it between A prime and B prime. Okay? Next, use the parallel postulate to construct a parallel line to this right here, and let its intersection over here be C double prime. So we're constructing line segments B prime, B double prime, C double prime, so that this line segment's parallel to this one here, B prime, C prime. And of course, then C double prime will be between A prime and C prime, like that. Well, now notice what we have. We have a pair of parallel lines here. And we have, if we extended them out, they would be lines, of course. And if we extend out this line segment, that makes a transversal to those parallel lines. Well, do you see like the letter F there? So the F property says that corresponding angles, these two right here, have to be congruent. When you have a transversal cutting a pair of parallel lines, corresponding angles must be congruent. I call that the F property. And so those two angles must be congruent. All right, now, what does that tell you about this little triangle here, A prime, B prime, A prime, B double prime, C prime versus A prime, B prime, C prime? Well, they're similar to each other. Why? Because of the AA triangle similarity theorem. That's our basic similarity, basic result, and we're going to use that to, we just did use that as a important step here. So now we have, those are similar triangles. Well, since this, so what does that tell you? That says that that the sides are proportional. So C prime over A prime, C prime A prime, that distance over C double prime A double prime, is got to be the same as the ratio of the sides on this side. But that over here, the ratio is K, so over here the ratio is K2. Well, if this length is K times B, divide by K, this is B. Well, now wait a minute. Now look at this little triangle up here and this one down here. They've got to be congruent. Do you see why? Because now we know that A prime C double prime is congruent to AC, and by side angle side postulate, these two triangles are congruent. Well, if they're congruent, then they're similar, and if this triangle up here is similar to the one down here, and it's similar to this one up here, then the first and last ones must be similar too, and that proportionality constant is K. And so we just proved the side angle side triangle similarity theorem. So notice we now have a side angle side postulate for triangle congruence, and then we have a side angle side triangle similarity theorem now as well. So now at this point we have two similarity theorems, and we might come back in a later video and look and see if there's another one as well.